Hello, welcome back to our course, Electronic System Design. So here we are on the sixth topic, that is component failure. Okay, why the components get failure. So how to describe the component failures. So in the last class, in the reliability analysis, we had seen three type of failures, right? Early failures, random failures, and so this curve we can see early failures, random failures, and wear out failures. Okay, so along this you can see now how the component get failure. Okay, so failure of electronic components drop to a few percent of their original values after burn in period, that is of 300 to 500 hertz, sorry, 300 to 500 hours, that is 2 3 weeks continuous operation. um, Maybe they lost their originality. Okay, so based on the environmental conditions and different sources also, the failure will be increased. Okay, so the end of the failure, early failures should coincide with the product leaving the manufacturer's test areas. The exponential distribution with its simple mathematical formulas introduces to apply to the random failures. So that is to the linear part of the bathtub curve. We can see in the bathtub curve, there is an exponential distribution curve also occurs. The failure rate we will be decided with the formula e power minus lambda t. That is the failure rate you can calculate. The random failure is not very accurate failure. Because of something happened, then immediately the random failure may get starts. The notation of randomness should be viewed statistically and based on the assumption that the time of failure for a given component cannot be predicted. Based on the statistical theory, you cannot assume that at what time the failure may be expert. You cannot predict, right? So the failure rate for every component and this every system becomes time dependent sooner or later. Okay. The reliability then depends on the accumulated service period and cannot be described with the exponential function. So we cannot decide. Exponential distribution is very important, but we cannot predict. Internal interconnects in the electronic components often suffers fatigue due to reverse thermal stress and become increasingly prone to failures. In addition, the surroundings atmospheres and impurities may enter through defects closer to alter state of each component. So here one more keyword, one more technical word you should say, that is the drift. So drift can be defined as the gradual change in the attributes over time that cause failure for a given loading. Okay. Drift is caused by chemical and physical processes inside a material or on its surface. The totality of these processes and their impact is called aging. Drift failures can be differentiated between monotonic and non-monotonic drift. So here, monotonic drift is characterized by the parameter that is a continuous value. It is continuous only varying in the same direction, crossing a predefined minimum or maximum value at some point. But coming to non-monotonic drift is characterized by both positive and negative variance of the parameter. So all we will see with the diagram. Next we will see about reference and operating conditions. So reference, so functional and environmental conditions can also significantly impact component failures. Therefore, failure rates without reference to functional and environmental conditions have little or no value. Operating conditions arises from the functional loads such as current, voltage, and power dissipations, and environmental conditions include all components stresses originating in the environment. So this includes based on their temperature, pressure, humidity, radiations due to mechanical stresses, that is vibrations and shocks. So all these will be make you to uh, suffer the component. So failure rates quoted by component manufacturers based on the reference conditions, if not otherwise specified using the concept of basic failure rates. As an engineer, as a development or design engineer, you should specify the failure rates of your components with a specific with some specifications that will help you, the user. He can manually test the failures of the components. Okay. So maybe my component, if you give more voltages and continuously burning, then the component will be deviate from its originality. We cannot break them. We cannot come back to its original position. So again, we have to replace it. So that is time taking process, and it will also we need to pay. So here we will see one example, that is the climatic and mechanical references stresses uh, based on the uh, based on this table. We can up we can get the basic failure rates. See, one is climatic conditions and one is mechanical stress. This is types of stress. This is reference stress. Suppose maybe my component get failure at ambient temperature, that is 40 degrees Celsius and 104-degree Fahrenheit. Okay. Relative humidity, under 30% of humidity. Maybe my get, so these are some conditions you should maintain for your for the component. Air pressure for electronic components negligible in the range 0.8602 to 1.60 to 10 power 5. Okay. So that is the reference stress is represented uh, 1.013 into 10 power 5 pantry audit. So that is the reference stress. And are coming to the mechanical stress, I already told you that is the vibration stress and shock stress. So here the vibration stress is maybe depends on two references stress. that is the frequency, and the range of 10 to 55 hertz, and the acceleration, that is 20 milli per second square, meter per second square, and at shock stress acceleration, that is 150 meter per second square, and duration is 11 milliseconds. Okay. So other stresses like wind, rain, snow, ice, dripping, spraying, splashing water or water jets, dust, the effects of pets, corrosive gases, radioactive radiations, temperature change, etc. So all these under stresses. So influence factors are used to determine the failure rates under given functional and environmental conditions. So influence factors also consider reduction, loading, or stress factors. So they are based upon the intended operating environment of components. So these factors we will be discussed here. So this is very important formula. You can calculate the failure rate of your component. Lambda B equal to lambda reference into pi V, pi 1, pi t, and pi e. So here lambda B, failure rate under operating conditions, that is operating failure rate. Lambda reference, failure rate under reference conditions, base failure rate. Pi V, voltage factor for voltage influence. Pi I, current factor for current influence. Pi T, temperature factor for temperature dependence. Pi E, environmental factor for environmental influences. So these are factors other than temperature such as humidity and vibrations. Okay, so all these multiplies, you will get the failure rate under operating conditions or operating failure rates. So if we want to calculate the failure rates of electronic components, the failure rate K of electronic components can be approximated by using this formula. That is very important. Lambda, that is failure rate, is approximately equal to number of failures by number of test units into period. Okay. So derating. Drift, how we can see, that is the next one, that is the derating. This technique also, this technique of operating an electronic device at less than its maximum capability is called derate. It is one of the key techniques for increasing reliability. The exponential degradation caused by temperature has a significant impact on failure rates. For example, operating temperatures of integrated circuit here I am considering, it is increased by 10K. The average time to failure is approximately off. So accuracy of failure rates can be defined here. Suppose failure rate of a components specified by a manufacturer's users and authorities. So for example, simple statement here I am taking the failure rate of film resistor, that is 33 into 10 power minus 9 failure per hour, is an unsatisfactory. Okay. So here operational and test conditions. So include functional stresses such as electrical, magnetic stresses, environmental stresses, ambient temperatures, humidity, mechanical, all we had discussed. So we have to limit the value for failure criteria, including drift failure criteria. And we need to consider their observational periods, stress cycles, if there is any necessary. And also we had to say its range of failure rates, that is the range that constrains the true value of a given probability. So calculated from the number of failures. Okay. So here you can also say that comparative reliability and weak point assessments can also be carried out with some specifications of single source. Okay, so the same concept will be applied to for the test also. So for example, durability of data for switches and relays. So we cannot specify directly, and they depend upon the type of contact loading as well as environmental conditions. So that is a difficult lifespan for the switches and relays. Okay. And for example, I'm taking a typical to failure rate for a relay, that is 10, 1 or 6 cycles, is equivalent failure risk, right? So the value should be multiplied with the cycles per time. Example, 1000 cycles. The failure rate is selected. All these things we had calculated some using the formulas, and we can predict some failure modes. So here the failure mode system are typically calculated from the failure modes quoted in the data sheets under the reference conditions and considering the actual stress and environmental conditions. The following conditions must be met to establish the system failure mode from the element failure modes. The functioning or failure of element independent of other elements. That is, there are mutual interactions between reliability values. So you cannot replace the component. It is very difficult task, right? So if module fails means you can replace it. Finally, conclusion is electronic components can fail due to variety of reasons, right? Including environmental factors, electrical stress, mechanical stress, manufacturing defects, and aging. So these factors can lead to a range of failure modes such as short circuits, open circuits, or performance degradations. So these all we will see, and we also provide some accuracy during the failure. What are the environmental factors we have discussed? That is the temperature, humidity, dust and pollution, vibration and mechanical shock, and radiation. So what is electrical stress? Over voltage, over current, electrostatic discharge, electrical overstress, incorrect wiring or polarity. What are mechanical stresses? Vibrations, thermal cycling, and physical impact. What are manufacturing defects? You can say soldering issues, contamination, defective materials. What is aging and wear out mechanics? Electromigrations, dielectric breakdowns, and corrosion. Corrosion means chemical reactions can degrade materials causing failures. And design related issues, insufficient derating, inadequate thermal management, and incorrect component selections. All these. Other than this, we can having some factors, power supply problems, human errors. So it is very easy to understand these failure modes, and their causes is crucial for designing reliable electronic system and preventing costly failures. So here you can say common causes of electrical components, very easy. Short circuits, open circuits, polarity reversals. So polarity we generally make it reverse in the initial state. Later we will be take care of that, right? Temperature, current leak, insulation resistance is where, okay. In some instances, poor constructions, that is installing heat sinks next to electrolytic capacitors may lead to failures. We already observed in some electronic vessels, we need to cool them. Even if the laptop also we make it a cool with the help of heat sinks. So failures also very important. Um, Mainly we can say the common causes of failures of electronic devices due to dust, vibrations, humidity and temperature. So here you can see major causes only due to temperature only. That is the main cause of failures of electronic components. Maybe less failure maybe occurs due to dust. And other than dust, Humidity. Due to humidity also, out of 100 percentage, 20% of failure may be occur. Vibration is less. Vibration failures are so less. Compared to all this, temperature stress is only more for electronic failures. Majority cases, you can say, uh, electronic failures are more due to temperature. So that is the main important formula you should be remembered. Thank you. So we will conclude the reliability analysis and also failure of electronic components in this class. Thank you. So we will continue the next class.